Okay, welcome back, friends. Um, so let us wrap up the boiling discussions. As you can see that so many things happen, right? And sometimes, in the very first year, I believe one person came up to me after the class and says, and, and his expression was, "Sir, पानी उबालने में इतना कुछ होता है?" हाँ, इतना कुछ होता है. So, a phenomenon which is so normal and which we have been observing since our childhood uh, actually has so much of so I mean so much of science behind it. Okay, just 1 minute, my battery is dying, so I need to plug in the charger. I'm sorry, friends. I think I was late by just 1 second in plugging my charger, and the computer just shut down. It doesn't give much time now. I mean, not even a minute. Okay, so now we are back. Let's continue from where we left off. We were discussing the pool boiling curve, right? And it's, as I said, it's quite fascinating. So much of things that are hidden just in one curve. Okay. Here, for example, this is the boiling curve that we have discussed. And so I'll come back to this thing called Leidenfrost point later. I wanted to show you some pictures. Okay, this is pool boiling. There are vapor bubbles that form. So in nucleate boiling, and probably in the later stages where you have more vigorous boiling, uh, I think you can all relate to this picture, right? We have all seen this. When your water starts boiling in your kettle, you can imagine this happening. Lots of vapor bubbles forming on this heated surface, and then growing and detaching. Okay. Then what happens is the bubbles adjacent to each other, they start coalescing, forming a bigger bubble that clings to the surface and slowly forms what is called a film. Okay. And that is what you see here. Right. So you see the formation of this film over here. Right. And this film hinders the heat transfer from the surface to the liquid pool. So this, my friends, is called film boiling, and the occurrence of this film is what results here. I cannot go back. Why? Results in this reduction in heat transfer that we see over here. Okay. Now this point, this Leidenfrost point, what is this point? When the entire heater surface is completely covered by the vapor film. Okay. So let me give you an example which we have all seen, where the person probably unknowingly uses this phenomenon. So have you seen, and I know several of you are from South India or anywhere, even here also. You have seen when they make dosa in the streets, right? First, what they do is, as the tawa or the pan starts getting heated, okay, the person waits before he puts in the batter. He waits till the point where he thinks, till the point where he thinks that the pan has heated up. I mean, heated up to a temperature which is acceptable and which is appropriate for cooking. Now, how does he know? We are talking about very high temperature. You cannot touch. You will burn your hand.
He splashes water.
He splashes water. Very good. And then what happens? Let me see how observant have you been? Yes, he splashes water and waits for what? Anyone?
The time required to evaporate, I guess.
Agree. Agree. He splashes water and then he sees that as soon as he splashes water, it pretty much boils off. Correct? He still does not put the batter. Okay? He still waits. And then when he then splashes water, the water doesn't boil off. What it does is it forms droplets and sort of dances around. Finally evaporates. Have you seen that? The water doesn't immediately boil off. It forms these small droplets, which has a very chaotic, like Brownian motion type, and then eventually it evaporates. When this happens, the person puts the batter. Okay. The reason is why. This is Leidenfrost point. Because what happens is he reaches a point where part of the liquid boils off, but forms this layer of vapor on the surface. And then the remaining liquid actually is in these droplets actually is dancing on that vapor film. Okay, so that is this Leidenfrost point. When this phenomenon happens, it may not exactly be Leidenfrost, but somewhere around, the person who is cooking, he decides that no, this has heated up enough, and so now I can cook. Okay. And what happens is when he now pours in the batter has water inside, the water will boil. But because of this high temperature, of course, as soon as he puts in the batter, which is at room temperature, the temperature of the surface will come down a little bit, but that's okay. You are still heating it, so it will eventually rise again. But what happens is this vapor film, there's a tendency for this vapor film to form, which prevents the batter from sticking to the pan. Okay. For people like me, Anadi cooks, or even for people who don't have that much of patience, what they do is to prevent the sticking, we pour oil, right? And then when the dosa comes out, it's oily on the sides, and we still have it. We take a paper napkin and try to soak off that oil to the best extent possible. But if you have actually seen the very good dosa makers, there are some actually South Indian joints even in Calcutta. South Calcutta has a lot of Tamil population, and I used to frequent those stores quite a bit. And those dosas that they come, it's like paper, and you won't find a drop of oil on top. Okay, all right. So this is the boiling curve. Now, I have always told you one thing, or not always, several times I've told you, especially during convection. If you want to get this curve, the x-axis is the temperature and the y-axis is the heat flux that you get, right? Now, let us say you are conducting an experiment, which is what Nukiyama did. Wataru Nukiyama, he's the one who came up with this boiling curve. Okay, we must acknowledge him. Nukiyama did an experiment. In the experiment, he took a pool of water, as you can see here. There were some heaters on the walls to keep it at close to saturation temperature. And then he had a wire going through. Okay. And he applied a voltage across the wire and let a current flow through it. Okay. So his was a power controlled experiment, not a temperature controlled experiment. Right? He was supplying power to the surface and slowly probably increasing the voltage, therefore the current will increase and the heat input and the I squared R losses will go up. So that's how it was a power controlled experiment, and he measured the temperature of the wire. Okay. So therefore, in an actual experiment of Nukiyama, the independent variable was the y-axis. The dependent variable was the x-axis. So therefore, what will happen? That's the question. What will happen? I told you before that it's much easier to do power controlled experiment. Probably we mostly do power controlled experiments. Temperature controlling is very difficult. The way we can do a temperature controlled experiment is, instead of this wire, I have a tube through which I pass some vapor at its saturation temperature, and I keep varying the pressure, and by that I can change the saturation temperature. Only then, that is one of the ways I can maintain an uniform temperature boundary condition and then vary it. Okay, extremely difficult. So temperature controlled experiment, it is possible, some people did it eventually, but extremely difficult. So Nukiyama's experiment was a power controlled experiment. I would also mention here that, as I said, he measured the temperature on the wire. How did he measure? How did he measure? Okay, was it putting on thermocouple? Not really. He was very, very smart. He measured the resistance of this wire. It's possible. The resistance changes with temperature. So he had started with platinum wires, and he had resistivity versus temperature characterized for platinum, and so he measured the resistance and could estimate the temperature. Otherwise, attaching a thermocouple on a thin wire is not easy, and this wire has to be thin because the resistance has to be high. I don't want it to be a very good conductor. I want it to generate a lot of heat, right? So this was Nukiyama's experiment, and this is Nukiyama's curve. What you see here is the boiling curve. But what was he doing? He was increasing Q of the heat flux at the surface. And so initially he saw, yes, there is something called natural convection. Then he saw pool boiling, etc., etc. That heat flux going up, up, up. And suddenly, when he came to this part, right, which is the critical heat flux, okay, the wire snapped. Okay, the wire just snapped, melted. He tried a few times. Platinum is expensive. Then he moved to nichrome, which is cheaper. Same phenomenon. And what he's saying is that after this point, which we are calling the Q double prime max or the critical heat flux, if he increases the heat flux even by a small delta amount, the temperature just jumps and jumps from like 30 degrees above the saturation temperature, let's say 130 degrees, to more than 1000 degrees. He says, what is going on? Tried quite a few times, and he found that again here, there's the wires burn out. So in a power controlled experiment, you would actually see this kind of a behavior. It goes here, and then suddenly it jumps like this and goes. Okay. So then what Nukiyama did was he said, okay, let me go very, very slow. So he did very carefully control the power input, was able to go up even beyond this temperature because nichrome melts at around 1500 degrees or so, 1200 degrees or so. He restricted himself there and said, okay, as soon as I am somewhere over here before this burnout point, I will reverse the heat flux. I will start reducing the voltage. Can I trace the path back? And to his utter surprise, he found that actually no, the path as he cooled during the cooling curve, the pattern or the plot looked something like this. It did not retrace its path. It actually came down and came down much lower to a much lower value than the critical heat flux. And then suddenly, when he came around like 120 degrees or so of superheat, he saw again a little decrease in the heat flux, saw a large decrease by almost 100 degrees reduction in temperature. Okay, so the curve looked like this. Okay, this is while going up, and this is while coming down. Okay, where have you seen such behavior before? Come on.
Sir, hysteresis loss.
Exactly. In magnetism, BH curve, the hysteresis. Right? So this therefore is also called, from that term, this is known as the hysteresis effect. the hysteresis loss and all that. There's no loss here. This is called the boiling hysteresis effect. Okay. So in a power controlled experiment, this middle portion cannot be obtained. Okay, you have to imagine. So that's why it is in a power control mode. That's why I've written it's absent in power control mode, and this is in dotted line. Not I have written, basically Incropera's book has this. Okay. However, some people later were able to do some power controlled experiments, sorry, some temperature controlled experiments, and they were able to get this part of the plot. Okay. Now somebody asked me, actually, I was teaching and someone asked me that I can visualize the heating part. Okay. This Qmax, as I already said, is called the critical heat flux, which is the maximum heat flux that you can get. This is a point of very, it's a very important point. I mean, how can I increase the critical heat flux? Can I, on all that stuff? Because normally unless you're talking about combustion and all, but otherwise in other cooling type of experiments, we do not go to above 1000 degrees. So, okay, furnaces, combustion chambers, yes, maybe film boiling is possible, but primarily for most practical applications, we want to be restricted to nucleate boiling. Okay, so this critical heat flux is something very important. Where does the onset of critical heat flux happen? That is important. Can I increase this from 30 to, let us say, 70? Okay, that would be good. All that stuff. So this is what your research on boiling, especially enhancing boiling, is focused on. Okay. Yeah. So what I was saying. So this person asked me that, I can visualize bubbles forming next to each other, growing and coalescing to form this vapor blanket or vapor film. But what is happening at Leidenfrost? I am unable to visualize that there is a film and suddenly it breaks up into bubbles. And actually, that is exactly what happens. It has to do with surface energy and all, but if there's a film and if you don't allow enough temperature difference, okay, the film just suddenly breaks up into smaller bubbles, okay, and then escape from the surface. And as it escapes, it takes away a lot of heat and suddenly the temperature goes down. That is exactly what happens in this part. Okay. All right. Now what I have is, let me see, not allowing me to end slideshow. Escape. Discard. Okay. So what I have here is, I have an animation. So let me see if I can play. This is a very nice animation with a very good commentary. Unfortunately, I had loaded it, but during that, when my battery died, I lost all of that. Chrome kahan gaya bhai? So if I restore, I should get back. Yeah. So let this come up. I don't know whether you will be able to get. Can you guys hear the sound of the video?
No, sir.
You cannot, no? Do any of you know how to do this in sharing? There must be a way. I know how to do it in Google Chrome and Zoom.
Sir, you need to share the tab. You are sharing the whole screen. So
Sharing the tab or the window, basically, right?
Yes, sir.
Okay. So now, is it okay? Are you able to hear the sound?
No, sir.
No. Yeah, so that's not the thing. Let me try again. Otherwise, what I will do is I will give you the commentary as I listen. Commentary is very nice. Include computer sound here. Yeah, you done it once before.
In English.
Now,
We tried a few online
Yes,
coaching
sir.
classes. A lot.
great. Okay.
Draw the pool boiling curve. We know that pool boiling is a mode of boiling where the fluid is stationary in the beginning with respect to the heating surface. To understand this boiling, let's consider an example of vessel containing some water placed on a burner. As the heat gets transferred from the bottom surface of the vessel to the stationary water, it starts rolling up and down. Then bubble formation takes place. And after some time, the water gets boiled. This process is a pool boiling process. Pool boiling takes place in different stages. They are free convection boiling, nucleate boiling, transition boiling, and film boiling. These different stages can be easily plotted on a heat flux temperature plot. X-axis represents the difference between the current temperature and saturation temperature of water, which is represented by delta T excess. And y-axis represents the heat transferred to the water per unit surface area of the vessel, which is represented by heat flux Q dot boiling. The curve OABCDE is known as the pool boiling curve of water. Here, curve OA represents the stage free convection boiling. Curve ABC represents the stage nucleate boiling. Curve CD represents the stage transition boiling. And curve DE represents the stage film boiling. Now let's understand each section of the curve one by one. Let's discuss about curve OA, represents the stage-free convection boiling. When we light the burner, heat transfer takes place between the vessel and water due to free or natural convection. We can see that the values of heat flux and delta T excess start increasing. And when the temperature of water reaches its saturation temperature, that is when delta T excess attains a positive value. Then boiling takes place. This stage of boiling is known as free convection boiling. Curve ABC represents the stage nucleate boiling. As we can see, nucleate boiling is divided into two parts. Curve AB represents liquid entrainment and curve BC represents critical heat flux. Now first, let us understand liquid entrainment. Due to continuous heating, we see that the value of delta T excess increases, and the bubbles are formed at the bottom surface of the vessel. These bubbles move upwards and carry some water along with them, but they collapse after covering some distance in the water. This is known as liquid entrainment. We see that the disturbance caused by liquid entrainment in the water increases the heat transfer coefficient, so the heat flux also increases. In curve BC, we see that as delta T excess further increases, the bubbles start forming at a faster rate. These vapor bubbles move upwards and merge to form numerous continuous columns of vapor in the liquid. The bubbles in the column then move upwards to the free surface, where they break up and release their vapor content. Due to this, the heat flux attains its maximum value, known as critical heat flux. Thus, the complete stage of boiling from A to C is known as nucleate boiling. Curve CD represents transition boiling. When the vapor of delta T excess increases beyond the critical point, we see that the heat flux starts decreasing. This is because a large fraction of the heated surface of the vessel is covered with a vapor film. This vapor film acts as an insulator as its thermal conductivity is lower than that of water. Thus, the value of heat flux attains its minimum value. Point D corresponding to the minimum value of heat flux is known as Leiden-Frost point. In curve CD, both nucleate and film boiling takes place partially. Thus, this stage is known as transition boiling. Curve DE represents the stage film boiling. We see that after the transition phase, the delta T excess further increases, due to which the vessel surface is completely covered by a continuous stable vapor film. Now, because of high temperature, we see that the radiation heat transfer takes place between the heated surface and the water through the vapor film. Thus, this stage is known as film boiling.
Okay, friends, I hope that animation was quite clear. Actually, this is very well done, this animation. Pretty much explains exactly what I did, but in a much more, much nicer way with proper graphics, animations, etc. Okay, any questions on the pool boiling curve? Everything clear? Okay. So the last mile is now simple. Let us wrap it up from here. So the pool boiling modes, especially for water, oops. I don't know what is happening here. Okay, let's just proceed from here. There's not much of full screen to see. The pool boiling modes, as we saw, natural convection, nucleate, transition, film. These have some regimes. These are regimes and all valid within a certain degree of superheat. So if it's less than 5 degrees, we really don't have boiling. We don't have bubble formation. It's primarily the convection currents inside. Then we have nucleate, we have transition, and we have film. Okay. So now, how do I solve these? So initially, if you are given a problem, you have to determine what is the level of superheat, and from there figure out which regime am I operating in or operating at. So for natural convection, all single phase natural convection correlations are valid. You have learned them. Okay. Nusselt number is something, so you can use exactly those, whatever we have learned under natural convection, except that it's not the fluid is water or the liquid, and you have to use those properties. For nucleate boiling, this is Rosenau's, the same Rosenau. Remember the Rosenau who corrected Nusselt analysis in condensation? The same Warren Rosenau, Professor Rosenau. He did a lot of experiments on boiling with different fluids, different shapes, different surface combinations, etc. And he gave this largely empirical correlation, where he says that the heat flux due to boiling, that Q double prime, which was there in the y-axis on the pool boiling curve, is given by this correlation. Okay, so one thing you can see is it is proportional to delta T cubed. Remember, in the temperature difference, the heat flux is proportional to the cube of the temperature difference between the solid surface and the water temperature. Right? So that is quite remarkable, right? Because in forced convection, conduction, even in natural convection, it was always proportional to delta T only. Natural convection, you can say, okay, the H is also proportional to delta T. So therefore, overall Q is maybe delta T to the power, I don't know, 5/4 or so, but cubed. That is also the reason why, if you take the log scale, it's a linear relation, more or less linear relation, not exactly. But if you look at Nukiyama, largely except at the top and bottom, middle part is largely linear. Okay, so these are all approximations, as we know, based on empirical results, and this is a correlation that he suggested. Now look at what all parameters does it depend on. It depends on the viscosity of the liquid, obviously, because the bubble is going to go through the liquid and there will be viscous shear forces at the interfaces. It is going to depend on the buoyancy force, so rho L minus rho V times G, of course, because that is building up because it's lighter than the liquid. Sigma, surface tension, because it is the surface tension force that is holding the bubble down, isn't it? The fact that it immediately doesn't detach from the surface and depart is because of surface tension, sigma. Surface tension versus buoyancy. When the buoyancy force is good enough, is strong enough to overcome the surface tension forces, the bubbles detach and move up. Okay. Then Cp, the specific heat of the liquid, times this temperature difference. Then HFG, that has to be there. Okay, Prandtl number of the liquid, and then this is, you can say, the tuning parameter also. It is CSF. It's some kind of a constant which depends on the surface and the fluid combination. Okay, and he gave a lookup table. If it's copper, water, it's something. If it is aluminum and whatever brine, it is something else, etc. So he has all this list. He has given that. So if you are given any problems, your CSF value will have to be given to you, or else you make some assumptions. Okay. This Prandtl to the power n, n for water was 1, and he said for other liquids, take it as 1.7. So all empirical. Okay, I mean, there's not much of scientific rationale behind this. Okay. For critical heat flux, we have two correlations. One is an infinite horizontal surface facing up. So Kutateladze and Zuber, they gave this correlation. The critical heat flux is given by this expression. And what you see is this last one, rho L plus rho V over rho V. Okay, to the power half. So that pretty much goes why have I written 1 here? Because rho L over rho V. Okay. So let's remove this. I don't know what I was thinking when I wrote this. Okay, so rho L is the liquid density, rho V is the vapor density. And if the plate is of finite size, then Leonhard and Heer, they gave another correlation. Okay. So this is what it is. These are again just correlations. You have to use it. Not much to understand here. Yeah, that's about it. Transition boiling, there is no suitable correlation, unfortunately. And for lead-in frost point, there is one correlation that is given. The Q double prime min is again given by something like this. Okay. And finally, for stable film boiling, it is exactly similar to film condensation. So therefore, for cylinders or spheres, it is given by a very similar correlation, except that the coefficients, which was like 0.72 and 0.69 or so in condensation, are slightly different. Okay. Otherwise, it's exactly the same. However, as we know that in as also you heard in that, the radiation effects become effect due to radiation. Okay. And finally, we use the average heat transfer coefficient is related to the convection and radiation coefficients by this. Okay, so if it's a film boiling problem, you first find out from this Nusselt number correlation what is the heat transfer coefficient due to convection. You find out from the heat transfer coefficient due to radiation from the second equation, and then the overall heat transfer coefficient is related to the two by this. And as you can see, this is like an implicit relation, right? Because you have H bar, the overall heat transfer coefficient on both sides. But however, if the heat transfer coefficient due to convection is much greater than that of radiation, if you're in that mode, then you can probably use H convection plus 3/4 H radiation. Okay, but otherwise this is, you have to use either solve it numerically or using trial and error. Okay, but again, this is pretty much playing around with correlations and nothing more. So in summary, we have studied the different regimes of pool boiling. We have looked at different correlations governing heat transfer at each region, and we learned the concept of critical or peak heat flux. Right? Okay, any questions? So we have 10 more minutes and we will quickly look at an example problem. Let's do that and then probably we'll have questions. This is the example problem. There's a boiling from outer surface of a horizontal cylinder inside water. It may be an electric heater. Diameter is 6 millimeter as shown here. And the surface temperature of that electric heater is 255 degrees C. This is water at 1 atmosphere. So the saturation temperature 100 degrees C. So we are asked to find out what is the total power dissipation per unit length. Unit length is in the third direction of the cylinder. So how would we do it? Assumption, steady state, etc., saturated water. These are the properties. The first thing, find out what is the delta T. What is the surface superheat? It is 155 degrees C, which is therefore in the film boiling regime. Remember this table? Greater than 120 degrees is film boiling. We are at 155, so we are going to assume that pool film boiling. If that is the case, the heat transfer per unit length will be H bar pi d times the surface superheat. Now H convection, you use that correlation and we get 238 watt per meter squared Kelvin. And H radiation, we get 21.3 watt per meter squared Kelvin. So I can definitely say that the convective heat transfer coefficient is much larger than that of radiation by more than 10 times. but it's not negligible. I cannot neglect radiation, because I neglect, I underestimate by 10%, which would be stupidity. If my aim is to maximize heat transfer, design a system for a certain heat transfer, and I end up underestimating that, then it's not good. I will oversize my heater. Okay, or I will be reporting lower values. So I cannot neglect radiation, but I can probably use the judgment that, this is significant enough, at least an order of magnitude higher. So therefore, I can probably use the simplified correlation, which said H bar overall is H convection plus 0.75 H radiation. Okay, I can probably use this. I can use my judgment. Okay. Or otherwise, if you want to do this, you can also solve this relation, and you get overall 254.1. Think about it, 238, and what is 3/4 of 21? 3/4 of 21 is like 15 point something. So 238 plus 15 would have been 253. I got 254, close enough. Okay. So if I had used the judgment, I would have got 253 point something. But if you actually solve this equation, which is not easy to solve, you can get 254. So therefore, the total heat transfer per unit length is Q double prime this times pi d. Therefore, H bar delta T times pi d, 742 watt per meter. Okay. All right. So thank you very much. That brings us to the end of our discussion on boiling, and that also kind of brings us to the end of our discussion, to the end of our syllabus actually, boiling and condensation. So what I will do is I will upload a problem sheet. It's not too many problems. I'll solve a few of them, again primarily correlation based, and just make sure you understand. Okay. So what we will do is tomorrow we will meet. If you have any questions, conceptual understanding, okay, not specific problems, and so if you have any questions, let me know. If you have specific problems where you are stuck in the problem sheet, send me an email. I will take it up one-on-one with you. I don't want to use the classroom hour to solve individual queries on problems. Okay, that can be a separate office hour. I am always available. If you send me an email, or if you want to set up a meeting for whatever, half an hour, 1 hour, I am always available. Okay, I may tell you that this time I am busy. Maybe I will suggest an alternate time, but feel free to approach me at any time, because teaching is my #1 priority. All right, now, Achha, tell me one thing. We decided on a date of the final exam. When was that? I know we had decided, I proposed 20th, but some of you were traveling back on that day and you wanted it a little earlier. What was the date?
18. The 18th.
18th. 18th is a Thursday, no? Yeah, tomorrow is 11th, 18th is Thursday. Okay, so 18th we will have it, and during the class hour itself then, 10 to 11. Okay, now tomorrow we will meet, as I was saying, we will go over any questions on any of the topics. Anyway, we did not get a chance to have any informal chit chat, so we will do a part of that. And I will cover a couple of concepts, okay, which I had to skip because of the brevity of time. But I will just cover those small things so that you know. Okay, especially for example, any of these, let us say, heat sink problems, finned heat sink problems, or flow through a tube, etc. The flow rate is given to you. But in an actual case, you have a heat sink or a bank of tubes, and you have a pump or you have a fan. Okay, how do you calculate what is the flow through that? Okay, so we will discuss all those. You have probably read a little bit. I don't know if you have read fan characteristic curve, system resistance curve. We will talk about all those. Okay, and a few other concepts like what is contact resistance. I think contact resistance we discussed a bit. What is spreading resistance, etc. Okay, what is Reynolds analogy? So we'll discuss a little bit of these things probably for 20-25 minutes. After that, I will take your questions. We will have some informal chat, and then we will bid goodbye to each other. Okay, So please come tomorrow. And for today, that's all we have. And thank you very much.